Good afternoon. Today we will continue our discussion on rotation. We already have discussed about how to describe a rotation. We describe it using the parameters of angular displacement, angular velocity, and angular acceleration. And the relationship between the angular position, angular speed, and angular velocity and angular acceleration, they are just almost the same as that of the rectilinear motion. So it's quite easy to remember. Okay, when you have a new equation that involves rotation, you can think of it with a structure that is very similar to that of a rectilinear motion. You translate the linear position, the coordinate x into the angle. You translate the linear velocity into the angular velocity and the acceleration into the angular acceleration. And so the argument just follow. Now we now would like to discuss about like to have a brief review on rotation on circular motion. Because rotation actually relies on circular motion, it's actually based on circular motion. Because every particle in a body, when the body rotates, every particle in a body will exhibit a circular motion. So that's why we want to have a review on circular motion before we go into our discussion on the rotational inertia. So let's have a brief review. Now this is the a uniform circular motion. We discussed it before in I think chapter 2, right? Now the mass, the point mass here, it is described by the vector r, and the vector r actually makes an angle theta with the x-axis. And because the circular motion, because it's a circular motion, the radius, the magnitude of this vector is a constant. So the radius is a constant, and the angle that the vector makes with the x-axis actually increased linearly with time. So the angle can be written as the angular velocity omega, which is a constant, multiplied by the time. So we can resolve the x, y, and y component of this vector, and we will rewrite the displacement vector in terms of the basis vector like this. Okay, the x coordinates is r cosine omega t, that is r cosine theta, and the y coordinates r sine omega t, that is r sine theta, right? And now, after one differentiation of the r, we find the velocity. The velocity is given by this. Okay, a straightforward differentiation. The cosine becomes a minus sign, the sine becomes a cosine, and do not forget we have additional factor of omega coming out due to the chain rule. And if you differentiate the velocity again, you get the acceleration. And the minus sign now become minus cosine. The cosine become minus sign. And so we take the common factor of -1 out, and there's another factor of omega, so we totally get omega squared. And since this is just the position coordinate, the position vector, right? The guy in the brackets together with this r is just a displacement vector. So the acceleration can be written as omega squared r, where r is the position vector. So you can see there are two important relationships coming out here. The first important relationship is the relationship between the linear velocity and angular velocity. The linear and angular velocity are just related by v equal to r omega, where r is the radius of the circle. And you can see from this formula that because the vector in the bracket is a unit vector, so the magnitude of v is just related to the magnitude of omega by a factor of r. Okay. And you can see from the acceleration equation that the acceleration magnitude is given by omega squared r, and the direction of the acceleration is towards the center. It's in opposite direction to the position vector. So that is directed towards the center of the circle. And that is, of course, the centripetal acceleration that you learn in high school. Now, but in rotation, we frequently encounter a change in speed. So the circular motion that the object exhibits may not be a constant speed, constant angular velocity circular motion. It may be the angular speed may be changing with time. So instead of just writing the angle as a function as omega t, where omega t is a constant, we actually will consider a general function of theta with respect to time. So the angle may change with time in a very complicated way. But as long as that is a circular motion, the radius doesn't change. Okay, we make a simplified assumption that the body is a rigid body. So you imagine every particle has a fixed distance from the axis of rotation. And so that means when the object rotates, each of the particle will go around the axis in a circle. And the radius of that circle will not change. Okay, but the speed, the angular speed that the particle revolve around the axis may change with time. And in that case, we already have discussed about it in chapter 2, right? We say that there are two components of the acceleration. The one component is the centripetal acceleration. This is exactly what we learned before for uniform circular motion. The centripetal acceleration is still given by omega square r, and the direction is towards the center. And we now use the component AR to denote that. AR means the component of the acceleration in the radial direction. And the minus signs means now the acceleration in radial direction is directed towards the center of the circle. And we also have the tangential component because the speed does change. So because of the speed change, so dv dt will give me the tangential component of acceleration. Now this speed change only when the circular motion has a changing angular velocity. Okay, when the angular velocity change, the speed of the particle also change. So v is equal to r omega. So now the differentiation acts on omega, and that becomes the angular acceleration. So the tangential component is simply given by the radius of the circle multiplied by the angular acceleration. Okay, so now you have two components of acceleration for this single particle. Now we also would like to write the kinetic energy of this particle, which is under circular motion. Now the kinetic energy is of course half mv squared. But as we say, in discussing about rotation, it may be more advantageous to use the angular quantity to describe motion. Instead of using v, we use omega, the angular velocity, to describe the motion, because omega is common for all the particle inside the body, if the body is a rigid body. So we write v equal to r omega, okay, and I squared it, so I got half mr squared omega squared. Is that right? Now we make a little bit change of notation because we want to generalize the idea to a system of particle. Now we are talking about a single particle in circular motion, but we want to describe a system of particle undergoing many circular motion around a given axis. So let us change our notation a little bit. Instead of calling this r, we call the distance between the particle and the axis. That is the perpendicular distance between the particle and the axis of rotation. We call that distance r pro. The subscript pro here means the perpendicular distance. It's not that the distance up or distance down, but a vector that joins the particle and the axis at right angle. Okay, so in that case, I rewrite instead of the r, I write the kinetic energy as half mr per square omega squared. Now this is just a slight change in notation, But why do we want to make this change? Because for a single particle, we can always make the particle to be on the XY plane. But imagine now you have a rigid body. You have a three-dimensional body. Not all the particles lies on the plane, right? There are some particle maybe higher and some particle may be lower. And so in measuring the distance r, you have to make sure that you are measuring the distance, the perpendicular distance of that particle from the axis of rotation. So that's why we make this change of notation. And with this change of notation, we are now ready to describe the moment of inertia for a body rotating about an axis. Suppose now we have a body, presumably a rigid body without any change in shape. So that body is now rotating about a certain axis, okay, with the angular speed omega. So omega is a common angular velocity shared by all the particles inside the object. So how do we write down the kinetic energy of this object? Well, we count individual particle. For example, there's a particle mi at this position. The particle undergoes circular motion around the axis, and its distance from the axis is ri per. Ri means the distance for the I particle, and the subscript per means now I am taking the perpendicular distance from the axis, and that is the radius of the circle of the circular path that the particle is now undergoing. Okay, and so the kinetic energy of that particle is of course half mi vi squared. And if we form a sum of all the particles inside this object, we have the total kinetic energy. But as we say, the linear speed can always represented as the angular velocity multiplied by what? This distance, ri per, right? This is the expression for circular motion, right? The linear speed and the angular speed are related this way. So instead of writing vi here, we write ri per omega. So the square of it becomes ri per omega squared. Now, if I take the square of this, I find that omega is common to all the particles. All the particles share the same omega, right? The angle turned about by each of these particles are the same in equal time. So omega actually comes to all the particles. So I can take it out from the summation. It's just like constant multiplying each of the term in the summation. So I can take the constant out. And what is left in the summation is summation mi per square. Now we now can nicely separate the information about the mass distribution and the axis of rotation. All this information is contained in this summation. And the information about how fast the whole object rotates is contained in omega squared. So we nicely separate the two pieces of information. One piece of information is about the distribution, how the particle in the object distribute around the axis of rotation. The other factor, which is omega squared, is give you an idea of how fast the object is now rotating. So it's nice to separate them, right? Because the first quantity is intrinsic to the body and the axis. And while the omega is just describing how fast the object is moving. Okay, so we separate that. And we would like to define this quantity, this summation, as a quantity called moment of inertia. We denote it with a symbol I. I is summation mi/ri per square. And I just want to emphasize that the I per, the subscript per here, means the perpendicular distance of a single particle from the axis. So you imagine this is a complicated object. Maybe it looks like a PHYS. And you have a particle mi here and a particle mj here. So each of these particles, they may have different distance from the axis of rotation. The particle mi will have a distance of Ri pearl from the axis, while the particle mj will have another distance of rj pearl from the axis of rotation, right? So you imagine the object now rotates about the fast now rotate about the axis of symmetry, and different particles simply have different distance from the axis. And if you multiply the mass of the particle with the square of the distance from the axis, and you form a sum of them, you got this quantity called moment of inertia. Okay. Now the important thing is to note that this quantity, it depends both on the mass distribution and also the axis of rotation. Why it depends on the mass distribution? Well, it's obvious. If you have a thrust that is very narrow, then all the particle will be closer to the axis, right? So you got, because of the r pearl square, you got a small angular moment of inertia. But if the thrust is very wide, then the particle at the base may be at a large distance from the axis of rotation. And in that case, you may get a large value for the moment of inertia. So it depends on how the mass is distributed, the shape of the object, and how far those particles are from the axis. It depends on that. That are intrinsic properties of the object. It depends on the shape and how far the particles are from the axis. But it also depends on the axis of rotation. Now, in this simple diagram, we assume, for example, the axis of rotation is about the symmetry axis, right? But it need not be so. You can rotate the whole object about other axes. For example, you can rotate the object about horizontal axis like this, or you may rotate the object about tilted axis like this, right? So for each of this rotation, the particle will have different distance from the axis of rotation. So in this case, the particle distance from the axis is totally different from the original case. So that's why the moment of inertia, this concept, it also depends on the axis of rotation. In order to well define I, you have to specify the axis that you are referring to. Okay. Without referring to the axis, the moment inertia is meaningless. It does not carry any meaning. If you say this quantity is moment inertia, you always refer to a rotation about a particular axis. Do you understand? Now, but sometimes the axis may not be inside the body. Okay. Now suppose I have my cup here, and I rotate the cup about my elbow, okay, like this. Okay, like this. The cup also has a moment inertia about this axis. This is the axis of rotation, right? And in this case, my axis of rotation is actually outside this cup, outside the body. But you can still calculate that, right? You count the particle here. Each particle has a distance Ri pearl from the axis. You form a summation of Ri pearl square. You get the moment inertia. Okay. Now with this definition, I can write the kinetic energy in a very nice way. With this defined as I, the kinetic energy is simply half I omega square, right? And that is a nice formula. When you compare this formula with the formula of the kinetic energy for the translational motion of a single particle, then you find them to be very similar. For a single particle in translational motion, you have the kinetic energy is half mv squared. Now for a rotation about a certain axis, rotation of an extended body about a certain axis, you have the kinetic energy is half I omega squared. Okay. Now the speed here is the speed of translation motion, while for rotation now we have characterized by the speed, how fast the rotation characterized by the angular velocity. okay, or the angular speed, okay? So the speed becomes the angular speed. And the mass of the single particle in translational motion now become the moment of inertia of the object. So the two formulas are quite similar to each other. And in fact, the similarity goes deeper. We will have more discussion on it when we discuss about Newton's second law for rotation. Okay. In fact, the I, this quantity, why do we call this moment of inertia? Why we call this inertia? You know the word here, inertia, because it's actually is a kind of reluctance for a body to change its state of motion. The body has some inertia to change its state of motion, just like the mass. For linear motion, the mass is a reluctance of the body to change its state of translational motion, right? If you accelerate the body, and if the body has a larger mass, that means you have to use a larger force to produce the same acceleration, right? So that is the inertia. But how about I? I somehow reflects the inertia of a body to change its rotational motion. So if you have a larger I, if your body has a larger I above a certain axis, that means it is more difficult for you to set the object into rotation. You have to use a larger moment or larger torque. Moment you learn in high school. Moment is a force multiplied by the distance, which is the turning effect of a force. You have to use a larger moment to produce the same angular acceleration. So the body becomes more reluctant to change its state. Okay, so that is a very similarity, a lot of similarity between I and M, which we will discuss it later. Which we will discuss later. Okay, so this is the meaning. Larger I. Heuristically, that means more difficult to make the body to rotate, or more difficult to stop the body from rotating. Okay. Now let's just have a very simple example. In this example, we only have 3-point mass. The 7 kg mass, the 8 kg mass, and 9 kg mass, and they are different distance from the axis. This is a top view. We look at the distribution from above the axis. Okay, so this is a top view. The axis pointing out of page now. And these are the distance. So what is this? What is this guy? Well, we list out all the mass, 7, 8, 9, and the 7 kg is at a distance 2 meters from the axis. So MRI per square, I square the R per. Square of 2 is 4. 4 times the mass 7 is 28, right? For this case, the distance is 3. For the 8 kg, the distance is 3. So 3 squared times 8 is 9 times 8 is 72. For the 9 kg is 1. The distance is 1. So 1 squared times 9 is 9. And we sum them up, these three numbers. We sum up these three numbers to get 109. So the moment inertia is 109 kilogram meter square. Now the unit for moment inertia is kilogram meter square. That is the SI unit. Because I have dimension of m here, which is kg, and dimension of length square is meter square. Okay. Now suppose we have two very small mass, two ball, very small ball, just like a point mass, okay? And they are connected by a rod, a light rod, a rod with negligible weights. So the mass, the two mass, each of has a mass of m. They are connected at two ends of a light rod, okay? At the ends, the two ends of the light rod. So now I have two axes. The first axis is about one of the mass. It's perpendicular to the rod, but it's exactly passes through one of the mass. So it's at the end of the rod. Okay, I call this axis A. So this is one of the axes. that I can think of. So you can now rotate the whole object about this axis. Now I just have a rod like this, right? I don't know how I can. So I have two masses here, right? One mass on which side. I can think of my axis of rotation to be here, so that the whole thing will rotate about this axis. This is a fixed axis, and now I rotate the whole thing about this fixed axis, okay, like this. But I can also consider that is the axis A, but I can also consider a rotation about the axis C, which is at the center. Now I imagine I have an axis at the center of the rod, and it's perpendicular to the rod. So when the object rotates about the center, it rotates like this. Okay. So now I have two axes of rotation. And so I would have a two moment of inertia. IA is different from IC, right? Because the rotation axis is different. I must get two different value for the moment of inertia. Let us calculate IA about this axis. Now the distance of this mass from the axis is 0 because the mass lies exactly on the axis. So it has a 0 distance from the axis, and so it does not contribute because m multiplied by 0 square, the distance square is 0. The second mass on the other end, it at the distance L, the length of the rod is L from the axis, so it contributes a term ml squared. So the sum of these two terms is the moment of inertia about A, and that's given by ml squared. How about if I calculate the moment inertia with respect to the axis C? About the center, each of the mass is at a distance L/2 from the axis, right? Because it's a midpoint. So each of the mass contribute a term m, the distance square, ml/2 square. And now we have two mass, so we have two terms. And so after calculating this sum, you find that the moment inertia is half ml squared. Okay. So the moment inertia is different in these two cases. They are different by a factor of 2. Okay. Is it easier to rotate the object about axis A or C? Do you know the answer? It's more difficult to rotate about A, right? Because A about the axis A has a larger moment inertia. That means if you want to set the object in rotation, you need a larger moment. Okay. To do the same acceleration on it. Okay. Now we turn the whole whole formalism into a continuous form. Because the summation formula we obtain are just for what? Are just for a discrete mass system. And it's not very convenient to apply that formula to a continuous distribution of mass. Normally in our everyday life, we are concerned with the object with a continuous distribution of mass. So we are now going to turn the formula into a continuous form that involves an integration. Now let's have a very simple example of a rod. I assume a uniform rod, and I want to find its moment inertia about an axis that passes through its end and perpendicular to the rod. And I suppose the rod has a mass m and length L. Okay. So I calculate the mass per unit length. Okay. The mass per unit is m/L. That is the density. How do I turn this summation into a continuous form? Well, we have summation mi/ri per square. Now we chop the rod into many small pieces. Okay. And the mass of these pieces, maybe I write it like this, so you can be have more understanding of it. Now these pieces, okay, has a length of delta x. Eventually the delta x become dx, and these pieces has a mass of delta mi. Okay, we call this I for consistency. The length is delta xi. The mass of this object, of these pieces, is delta mi. So what would be like? What would be this formula? This formula will go to summation I. Now I have these pieces delta mi, and this pieces is at a distance xi from the axis, right? So now I have xi squared. So I form a summation of all the pieces from this end to the other end, and that gives me the moment of inertia. Now, imagine what will be the case if I change to the continuous limit. It will become like this. In the continuous limit, the delta m will become dm, and the x squared here will become the you can call it r squared, or you can simply call it x squared, because we only have the x-axis in this case. So it becomes x squared dm. Okay, x squared dm or r squared dm. Doesn't matter. It's just this distance. Okay. Now the d goes with the delta here, because I'm considering small pieces on the rod. Okay. So it is r squared dm. Okay. The differential comes from the d, comes from the mass, because I'm considering a lot of small pieces of mass along the rod. Now, how do I calculate this integral? Now, the distance for the pieces, for these pieces is x, right? The r is just x. So now I have x squared. How about dm? How do I find dm? Well, I can find quite easily, because as I say, the density of the rod, the mass per unit length, is m over l. So the mass in the length dx, I call it dm, is just the density multiplied by the length of the segment, right? I multiply the mass per unit length by the tiny length of that segment. I got the tiny mass of that segment, right? So that is the simple ratio. So I now put it back. I now put this quantity back. I put to replace the dm, and everything now becomes expressed in terms of x. Okay, so I can do the integration. The integration is, of course, from x equal to 0, which is along the SSA, to the other end, which is x equal to L. So I do the integration from x equal to 0 to x equal to L, and I come up with the integration of x squared. The integration of x squared is, of course, x to the power 3 divided by 3. And so that gives me 1/3 of L cubed. And after canceling one of the L here, I got the final answer as 1/3 of ml squared. Okay. So that is the moment inertia of the rod about one end. Now that we would like to discuss an important theorem in calculating the center of mass. The moment of inertia. Now I know that this slide actually looks a little bit scary. So I better skip, not skip, but I better tell you the result first, in order for you to understand what is happening before showing the proof. Okay. Now what I'm going to say is like this. You now have two axes, axis A and axis C. They are parallel to each other. Okay, they are parallel to each other. And the axis C passes through the center of mass of the body. Now you have an extended body. You have two parallel axes, and one of the axes passes through the center of mass of the body. So what we are going to find, is a relationship between the moment of inertia about axis A and the moment inertia about axis C. So we are going to find the relationship between IA and IC. And it turns out that they are related in a very simple way. The moment of inertia about axis A is equal to the moment of inertia about axis C. Now, axis C passes through the center of mass. Note that. Is equal, IA is equal to IC plus this term. This term is what? M is the total mass of the object. And R pro, this capital R pro square, is the distance, is the perpendicular distance between the two axes. Simple enough. Now, but you should know that the IC is on the side of MR pro square. Okay, IC is the moment inertia of that passes through about the axis that passes through the center of mass. If IC is equal to R pro square, then it just gives you the moment inertia about the axis A, which is separated from C by a distance of R pro. Okay. Now the theorem also show that because I know this MR pro square is always larger than 0, right? So that means IA is always larger than IC. Is that right? Because this quantity, no matter how the axes are rotated, are oriented, this term is always larger than 0, and that means IA is larger than IC. So that means about all the parallel axes, that passes through the body, the axis that passes through the center of mass of the body has the smallest moment of inertia. Okay, the moment inertia about the axis that passes through the center of mass is smallest. Any other axis that is parallel to this axis has a larger moment of inertia. That is the conclusion that you can draw from this formula. And this is called the parallel axis theorem. The parallel axis theorem. Now I will show you the proof now, but the proof is rather abstract. You need to have some sense of mathematics, good sense of mathematics to understand it. But even if you don't understand the details of the proof, you can still use this formula to help you solve many problems about moment of inertia. After knowing the moment inertia for an axis, you can now use this formula to find the moment inertia about another axis that is parallel to the original axis. That's why this formula is so powerful. Now I show you the proof now. We have axis C and axis A. Axis C passes through the center of mass, right? And the distance between the two axes is R pro. Now I define the R pro to be a vector that points from axis A to axis C. Okay. This vector is perpendicular to the two axes. Okay. Now we have a certain mass, we chop the large object into many small pieces, and each pieces for the eyepiece we call the mass mi, and the vector that points from the axis A to this mass is Ri pro, while the vector that points from the axis C to the same mass mi is Ri pro prime. So the prime always refer to the position vector that points out from the axis C that passes through the center of mass. And R without the prime, it tends to stand for the position vector that points out from the axis A. Okay, is that clear? Now you should know that the vector does not come from the origin. It actually comes from the axis. It is a vector that is perpendicular, that goes to mi, but is perpendicular to the axis. So that's why we use a subscript per. It is not the vector that comes from the origin, but it is the perpendicular vector that originates from the axis itself. Okay, so you draw a perpendicular line from the axis to that point, and you have Ri pro. for axis A. If you do the similar for axis C, you got Ri per prime. Now, if you look at this diagram from the above, okay, you imagine yourself to have a top view of this diagram. You look at this on the top, and you will see the axis A and C running out of the page. And you will also see this three vector R pearl, Ri pearl, and Ri pearl prime. They form a triangle like this, right? Is that right? You can see from this triangle, okay, the three vectors. If you neglect the heights, right? If you press the three vectors onto the same plane, you can see they form a triangle like this. Is that right? Now let's go with the direction. The moment of inertia about axis A is summation mi Ri per square. That is the definition. But since the vector, the three vector form a triangle like this, the Ri per vector can be written as a sum of the capital R per vector and the Ri per prime vector. Okay, so capital R per plus Ri per prime is equal to Ri per. So I can replace this Ri per by capital R per plus Ri per prime. And I take the square root of this, just like here. But you should know that what I mean by square is a dot product of this vector with itself. Okay, so I form a dot product of this vector with itself. The first term is, of course, R pro dot R pro, and so I got R pro square. The last term is Ri pro prime dot Ri pro prime, so I got Ri pro prime square. But there are two exchange terms, and the cross term gives you capital R pro dot Ri pro prime, and we have two of this term. Okay, so you are just doing the simple algebra with a plus b square. A plus b square is a square plus b square plus 2ab, right? But the only difference is now it is a vector, and the dot product will give you a dot product between the two vectors for the cross term. Okay. Now the summation can be separated into three terms. The first term is summation mi capital R per square. The last term is summation Ri mi Ri per prime square, right? And the middle term is summation of this ugly guy. Now we look at each of this term. Now the first term, summation mi multiplied by capital R per square, because the R per square is a constant and it can be taken out of the summation. So we are left with a summation of mi, but summation mi is what? It's the total mass of the object. Is that right? So we have capital M as the total mass of the object multiplied by R per square. How about the last one? The last one is summation mi Ri per prime square. And that is the moment of inertia about axis C, right? Because this vector points from the Ri per prime points from axis C outwards. So the summation of this, summation of mi Ri per prime square, is just the moment inertia about axis C. So this is IC actually. And what is this term? What is the cross term? Now for the cross term, we have capital R per dot with this Ri per prime, right? And since the capital R is a constant vector, it can be taken out of the summation. We can form a summation of mi Ri per prime first, and then I form a dot product of the sum with the vector capital R per. Is that right? I just take this constant term out, right? But as I proved in the last chapter, because the Ri per prime vector is a vector that points from the center of mass, right? It's a vector pointing from the center of mass. Okay, so the summation of this vector is 0. Okay, and that is proved in the last chapter when we discussed about center of mass. Do you remember that? Do you remember this formula? We proved that in this formula. we say summation I CM is equal to 0. This is the property of center of mass. If you have your origin located at the center of mass, and you point to different pieces, and the vector is RICM. The subscript CM means the origin is now at center of mass. Okay, if I have MI here, I have a vector that points from the CM, the center of mass, to that point. I call this vector RICM. And you form a sum of this over the whole body, you will get 0. And this is in fact one of the component, right? Because I only consider perpendicular component. But since this is a vector equation, it's true for all three directions. So if you only take the perpendicular component, it will still hold, and that will give you 0. So this term vanish. Okay, this term does not contribute, and you eventually have IA equal to IC plus capital MR per square, and that is exactly the formula you got here. Okay, and I've explained to you the meaning before. Okay. Now, having some difficult proof, if you cannot manage that, no problem. You just understand that and try some of the application. Now, for example, we have calculated the moment inertia of this system, right? About two axes, about axis A and axis C. And obviously, axis C is just the axis that passes through center of mass. So the two moment inertia are related this way. IA equal to IC plus M capital R per square. Well, R per are the distance between the axes, and now for this case, the distance is L/2, right? So I now can apply this formula to check whether the per-axis theorem is satisfied. Now, suppose I know IC. IC is half ml square. We found it before, and we put IC here, right? And the total mass of the system, not just the single mass, the total mass of the system is 2m, because each of the mass has a mass m. The distance between the axis is L/2, so we have 2m multiplied by L/2 square. When I add it to the half ml square here, I got ml square. And this is exactly the moment inertia about axis A that we found previously. So after this calculation, you find that in this case, the formula, the parallel axis theorem does hold. Okay. Now, before our break, let us have understanding of this. In our previous discussion, we have used an integration to find the moment inertia of a uniform rod about one end, right? The axis is A, is the axis that passing through one end of the rod, and I find that the moment inertia 1/3 of ml square. Is that right? Please use the parallel axis theorem to find the moment of inertia about an axis that passes through the center of the rod and perpendicular to the rod. Okay. Now I give you 2 minutes to do it. It should be easy if you understand the formula well. Okay. You just tell me the answer. Somebody have already found it. Yeah, the answer is correct. Have you find it? Two of you already reply. Now let's do it together. Okay. The answer is quite simple. We prefer to use this. Now we have this formula, right? IA. Oh, sorry. IA is what? IA is 1/3 of ml square. Is that right? And m is what? The mass of the rod, and the perpendicular distance between the axes, r pearl, is what? It's alpha 2 squared. Is that right? It's alpha 2. So we have alpha 2 squared here, plus IC. So that means IC is equal to, this is a 2 here. And I now extract the factor of ml squared out, okay? And inside the bracket, 1/3 minus what? 1/2 square, right? So 1/2 square is 4. Is that right? So 1/3 minus 1/4 is 1/12 ml squared. Okay. So you got the answer. Now, but there is another method to find IC. That because moment of inertia is a sum, right? You can consider the whole rod to be a sum of two smaller rods, and each of the rod has a length alpha 2. So you consider not a single long rod about its center, but two smaller rods of moment of inertia about one end. Okay. Now, if you chop the rod into half, then you will be finding the moment of inertia of that smaller rod about one of its end, right? And because that is a sum, that's a summation. So if you add up the moment of inertia of that two smaller rod, you get the moment of inertia of the large rod about the center. Is that right? Now, so we proceed like this. We know that we have found before that the moment of inertia of a rod about one end is 1/3 of ml squared. So we apply that formula, 1/3 of ml squared. But we now apply it to the smaller rod, not the long rod, right? Because the center point here is the end of the smaller rod, right? So we can apply this formula. But for the smaller rod, the mass is not m. The mass is m/2 only. And the length of the small rod is alpha 2 instead of L. So we have 1/3 m/2 multiplied by alpha 2 squared. And since we have two such rods, we add the contribution together because that is summation. Okay, so we multiply a factor of 2. And after some calculation, you find that exactly equal to 1/12 ml squared. Okay, so this is just to remind you that the calculation of moment of inertia is a summation. And for summation, you can just break it. You can just break the summation into the sum of moment of inertia of different objects added together. In this case, we break the large rod into two smaller rods about one end. Okay. Okay, is that okay? Now, I think it's better for us to have a break here. That's a long lecture. The concept is rather subtle here. So let's have a break for 10 minutes. And after we come back, we introduce another theorem of moment inertia called perpendicular axis theorem.